thanks everybody for joining the meeting today. We'll have a presentation on Catalyst, a compiler for hybrid quantum programs. Please take it away.
Awesome, thank you, Jack. Can you hear me well? Just a quick audio check. Awesome, perfect. Yeah, so thank you for having me. It's a pleasure to be here and engage with the MLIR community. I've been a fan for a while, so my name is David Ittah. I work for a company called Xanadu, which is named after the song, not the movie. And we are primarily a hardware company based in Toronto who builds photonic quantum computers. And we've had lots of growth in the past few years. We are now over 170 employees working on this with $1 billion valuation after our last funding round. And primarily we build quantum computers, but there's also a sizable software effort, which builds open source software for the quantum community. And I'm the technical lead on the Catalyst project, which is a novel compiler for classical quantum programs in Python. And if anything is unclear throughout the presentation, please don't hesitate to jump in. And we can also discuss more at the end. So I'm sure you've heard lots of hype around quantum computing. I don't really want to give another poor explanation of how quantum computers work and so on, but maybe just tell you what you need to know from a compiler engineering perspective. And the first thing you may ask is, well, how do people design quantum algorithms? And the most common model that people use is the quantum circuit. If you think back to the early stages of classical computing and imagine, writing or designing Boolean logic circuits, maybe it's sort of like that. So you have a couple elements. You have the quantum memory, which are your qubits. They should be individually addressable, and you should be able to initialize them to a known state. And then, of course, you want to manipulate these states in some ways using logic gates, so quantum logic gates. And you may recognize some of these elements from Boolean logic circuits, like this controlled NOT operation. And in fact, Boolean logic is a subset of quantum logic, although with a restriction. So technically, reversible Boolean logic is a subset of quantum logic. For example, the AND gate is not a valid quantum operation, but the reversible version of it is, which is the Toffoli gate, or a doubly controlled NOT operation. And what's important as well is that some of these operations can be parameterized, like this one labeled Ry. It has this 5-parameter angle, and we will use those parameters for certain algorithms. Finally, if you want to get any information out of your computation, you need to perform measurements, and it's the only way you can get information out. And you also need to be aware that measurement will affect the state of your memory. So it's not only reading it out, but it will also have an effect on it. And if you're wondering, well, this representation, it looks very static. Can you have dynamical elements in your quantum circuit? And this is a legitimate question because these circuits are essentially directed acyclic graphs. And so this severely limits the control flow graph that you can have in these, so there's no control flow graph. But it's one of the core components that people use to express quantum algorithms in. So how do we actually express algorithms or implement them in software? And it's actually very close to what we just saw. The vast majority of users choose a Python-based framework. The one used here is called PennyLane. It's our open source quantum computing framework. And they implement the circuit or algorithm in a domain-specific language provided by the library. So typically you want to specify how to actually execute the quantum component of it, what kind of device you want to use, hardware or a simulator maybe. And then you write a meta program that describes the computation. So there's other approaches, quote unquote, like real languages, like Q#, that are a language in its own right. But most users actually prefer this sort of embedded domain-specific language approach. And then depending on the framework, you can do additional things like embedding your quantum computation into additional workflows, even machine learning workflows. But we'll see more about that. So I'm not really an algorithms person, but I do want to briefly mention maybe what you can do with a quantum computer. What are some of the applications? And one of the common misconceptions is that quantum computers can just accelerate any classical algorithm, maybe similar to how a GPU would accelerate it if the algorithm can be parallelized in some way. But this is really not true. So you actually have to design and carefully design an algorithm that specifically takes advantages of the new quantum computation elements that you have access to. And this is actually quite difficult in an active area of research. You have some bespoke quantum algorithms, these textbook algorithms, which have been known for a while. And they, some of them at least, have a proven computational advantage over any possible classical algorithm, which is great, but there aren't that many of them. You have the factoring problem, factoring prime numbers, which there is a known efficient algorithm for, a quantum algorithm, which would allow you to break asymmetric encryption, for example. And there's some others, but active area of research are simulation algorithms, so simulating quantum chemistry with the idea that this will help you in designing new materials or other products. So for example, car manufacturers are interested in it to improve their batteries. And there's also a whole field focused on hybrid quantum classical computing, especially with machine learnings. You could maybe have even a quantum neural network and some focus there might be differentiable programming. So I'll leave it at that for now. But let me talk a bit about why we started working on Catalyst and describe the progress that has been made in compilation architectures. So early quantum computing frameworks, what they were getting wrong is that you start with this meta program in Python, as I mentioned, and you certainly can have dynamical language constructs like loops. You can use those, but they're not actually part of the quantum program you're describing. They're part of the meta program. So what happens before you can even think about executing your quantum program is that you need to run the meta program. So you supply inputs to the parameters, you run the library code, and in the process, you generate a sort of data structure that represents the quantum circuit. This could be a DAG, or it could be a list, or some other data structure that is equivalent to a quantum circuit. And crucially, there's no more loops. The number of qubits, so the number of memory you'll need is exactly known. There's no control flow graph. And yeah, after you have this data structure is when you perform compilation, quote unquote. So quantum compilation, typically you perform some gate optimizations and maybe some specific hardware lowering. And maybe at this point it's apparent what some of the issues are, or maybe it doesn't seem like a big deal, but let's just see what happens when you scale it up. So remember, the factoring algorithm Let's just say you wanted to use it to break RSA. Modern RSA recommends about 2,000 bits for your encryption keys. And certainly the algorithm will scale with this number of bits. So there's this paper back in 2020, which measured compilation time for two of these Python-based quantum computing frameworks on Shor's algorithm. And they measured the scaling against the number of bits and compared it to a prototype for quantum compilation in MLIR. So I don't want to focus too much on the actual numbers. By now the results, I'm sure, are somewhat outdated, but just want to illustrate the issue with this graph. So the program size, or if you flatten it out, like the circuit representation, it scales to the power of 4 with the number of bits that are needed. And if you actually, look at the compilation time in these Python-based frameworks, it scales up very quickly. So even 11 bits here, you're already reaching a compilation time of minutes, and scaling this out to 2,000 bits, you get into territory of thousands of years. Whereas the representation in MLIR that contains the program as is, so as the user expressed it with control flow and so on, the compilation time there is constant because it doesn't, the size of the representation doesn't scale with these parameters like number of bits. And you can do all this without necessarily losing much in optimization potential. So I don't want to make any sweeping claims here that obviously the more information you have, the better you can optimize. But you can still perform effective optimization on a representation of the program that contains control flow and is much more compact. So the flat circuit generation approach does not scale. And rather than representing circuits, well, what have people been working on in the meantime? So I myself started working on this problem in 2020. I was a student at Ittah Zurich, and we were looking to design a next generation quantum IR for hybrid computing. The MLIR paper had just come out, which was really fortunate timing, which led to us designing one of the first quantum dialects in MLIR. And it was also followed by many others, such as one out of the Oak Ridge National Lab. They worked on this concurrently, and there were also others. And at the same time that we were working on MLR, Microsoft announced a new quantum intermediate representation called QIR, which is based on LLVM-IR. So this IR was later transferred to the QIR Alliance, which now has many industry members. And since then, there's industry players who are slowly adopting full-scale hybrid IRs like these. So there's the QCO project, again, out of Oak Ridge. We ourselves have just released Catalyst earlier this year in preview. And NVIDIA just released their QDOR quantum computing framework, which uses MLIR as well. And there might be more that I missed. So let me briefly linger on why we did choose MLIR. Some people may say, well, what about quantum assembly? I've heard of this thing called OpenQASM. And OpenQASM is, in essence, the first version was like a textual description of a static circuit. And now they've started adding some classical instructions to it, some dynamic elements, but in a limited fashion. And in my opinion, it's the wrong approach to add these classical elements from scratch to quantum circuit representations, when instead we can benefit from a rich ecosystem around classical compilation, which can already accommodate quantum abstraction. So OpenQASM has no in-memory representation and no transformation infrastructure. So to me, it's not really an IR, but it's useful as a de facto standard for tool interoperability. and people use it in that way. What about LLVM then? So this QRapp project, well, I'm sure I don't need to tell you this, but I much rather implement domain-specific abstractions in MLIR rather than LLVM. QRapp uses opaque pointer types for their custom data types, and all their operations are function calls. Whereas in MLIR, you can benefit from the custom types, operations, attributes, assembly, and so on, structured ops, which I really like. But the two aren't necessarily exclusive, as we'll see in a bit. But I think MLIR will win out here in the long run. So let's talk about Catalyst. So Catalyst is intended to work with PennyLane. PennyLane, as I mentioned, is our software framework for quantum programming in Python. And it has a strong focus on integrating with the machine learning ecosystem. It supports hybrid computing models. And I think this is what allowed it to become the second most popular framework for quantum computing. But there are some issues. So these issues that we intend to solve with Catalyst. One very important one is reducing the latency between classical and quantum components. Typically, you communicate a quantum circuit, you send it off to a hardware provider, maybe in the cloud, you wait for the results, and maybe you change some of the parameters, and then you do this again. And if you do this a lot of times, this is very slow. So we need to solve this somehow. The second issue, compilation bottlenecks. As I mentioned already, we want to scale to very large circuits, so we need a more efficient representation. Then we want to go beyond what is possible with the circuit representation. We want fully dynamic quantum programs that adapt the execution to intermediate results. So, maybe it can decide to execute different instructions depending on some classical computed value, or even this paradigm where you repeat a certain sequence of instructions until you get the desired outcome that you want. So you would need to support unbounded loops for this kind of scenario. Many people are interested in heterogeneous execution. So how do you distribute computation across the host machine, accelerators, and quantum computers? And finally, we want a unified architecture for compiling quantum and classical programs. So just to illustrate some of these points, this is an existing, this is a program in the PennyLane framework, and you can already access hardware devices, for example, like the bracket, via the bracket service. And as I mentioned, though, each execution is sent in individually, so the latency is very large. You can already use just-in-time compilation, but the compilation pipeline for the quantum and classical parts are completely separate, and JAX, in this case, will be completely oblivious to any of the quantum components. You can also already use control flow, but it is fully unrolled, and if the bounds somehow depend on the function parameters, you would recompile this every time for new inputs, which is also very excessive. So Catalyst is not only a compiler with under the hood changes, but it expands the level of dynamicism that is normally only supported in fully featured compiled quantum programming languages. So I don't want to go too much into that because I want to show you some under the hood stuff. But I just want to briefly mention one of our core requirements, and that is make it as easy for our audience as possible. Our audience is researchers. They want to quickly prototype, they want to debug, and scale up the computation when needed. And so we wanted to make sure that Catalyst is as easy to use as possible. And for many applications, it's just as easy as adding a decorator to your existing hybrid workflows. Okay, so this is the Catalyst stack. There's a front-end component to it. There's a compiler core, and there's a back-end code generation and execution environment. And we wanted to make sure that each component is as independent as possible, so you can swap out the front end or the back end or whatever you want. And let me briefly give you an overview. So the front end is concerned with capturing programs in Python. We do this via tracing. So for this, we use the JAX framework, which does a great job at this. And we extend JAX to represent all the quantum instructions as well. From JAX, we then go to MLIR. So JAX generates HLO dialects, which we can then lower to standard MLIR dialects. We have a new quantum dialect that we use to represent quantum abstractions. We use the control flow dialect extensively, and we also have a big focus on autodiff. So we have this gradient dialect, which implements some quantum specific differentiation techniques. At this level, we of course perform optimizations on the quantum and classical program as well. Then for the code generation, we lower to LLVM. We use LLVM for code generation, generating a binary, and the runtime that we developed supports the binary. It provides all the quantum execution components that the binary requires. So right now we only support simulators, but really we're looking at supporting a variety of different devices. And the bottom part of the stack is really still the one that's the most in flex, I would say. But some of the important features here is that you can have device-host interactions and they can affect each other. And yeah, I would say that's one of the most important features here. Okay, so how do we convert Python to MLIR? This is maybe not actually that easy, because originally we played with a parser to kind of parse our domain-specific language and convert that to MLIR directly. But you run into the issue of the dynamic nature of Python. And so instead, we leverage JAX. So we extend the JAX internal representation, which is called JAX-PR. And this is quite easy to do, actually. So we define a new data type, in this case, a qubit data type, and we define an MLIR lowering for it. In this case, we just lower this in opaque type in the quantum dialect called bit, although in the quantum dialect itself, it's not an opaque type. And yeah, you just register the lowering, and the JAX infrastructure does the rest. Of course, we need to add new operations, which is similarly straightforward. Operations are called primitives, so we can define a new one called unitary, which is some operation that takes in a matrix and applies it to qubits. And you need to define its abstract evaluation. So what does that mean as well? What are the output types of the operation? And this is where we already convert the quantum program to observe value semantics. So we want an instruction to take in qubits and output new qubits, or rather new qubit states. So we do this here, and the value semantics helps us leverage the MLIR infrastructure at the next level. So again, you need a lowering for operations. You can do this quite easily as well. So we use the Python bindings for MLIR. So this is, let's say we use the bindings for our custom quantum dialect, and we can just instantiate operations from the dialect that way. And JAX will mostly put everything together. I mean, there's more glue here required, but that's the gist of it. So looking at the quantum MLIR itself, as mentioned, we added a quantum dialect. Adding operations to the dialect is very straightforward. So this is the unitary op that I mentioned. I'm sure you're all familiar with this sort of thing. And then we can run optimizations on the quantum dialect. For example, if you wanted to fuse two of these unitary ops together, we can leverage the MLIR infrastructure for this. So in this case, let's say we wanted to fuse these two unitary ops. Let's just check that two of these ops are actually succeeding each other on the same qubits. And if they do, let's say we can then combine the matrix argument that they have. So we rewrite the sequence of two unitary ops into a single one by multiplying the matrices together. So this is just an example of how you would use MLIR to write quantum optimizations. A big focus of ours was automatic differentiation. So we did add a gradient dialect, and it implements, as I mentioned, quantum differentiation techniques. So let's look at that a bit in more detail. So a hybrid quantum function, if you will, you have a function from some real numbers, and it outputs some real numbers as well. So this is important. But typically, the function arguments will be processed in some way. So if the user writes this function at the top here, we can split it into a composition of two functions: the parameter processing of the function and the pure quantum part of it. So once we split these two components, we can then differentiate them separately. So the classical part, you would typically use backpropagation to differentiate that. And for the quantum part, we use specific quantum techniques. So this is kind of like the scheme of how we approach autodiff on hybrid programs. There's some techniques that are compatible with hardware even to perform quantum differentiation. A popular one is called parameter shift, where you just modify the gate parameters. And we did a lot of work here so that we could perform this shifting dynamically at runtime, rather than just generating several copies of the same program just with different parameters. Simulators can also benefit from different differentiation techniques, essentially backpropagation. So the adjoint method is essentially the same as backpropagation, but it doesn't store any intermediate values. Because quantum computing is reversible, you can just redo the computation in reverse without storing any intermediate values. And so this is really beneficial for memory, especially because quantum simulation requires a lot of memory. So with the adjoint method, you can go beyond what you could do with backpropagation. Yeah, so once you compute Jacobians for your classical and quantum parts, you can just combine them together to get the full, well, well, hybrid gradient. And okay, so what's next? I mentioned the device compilation and execution is a big focus of ours. So really here we want to think more about, well, how do we support different kinds of hardware? How do we do device-specific compilation? This will be a big focus of ours this year, and move towards the goal of being able to compile for quantum processors that are co-located with co-processors and execute hybrid algorithms efficiently. The second part is optimization. So as I mentioned, Catalyst is in preview, and really there's a lot more to be done to optimize for speed and add a lot of quantum compilation algorithms to the MLIR ecosystem. So this will be one of our goals. Yeah, thank you very much. Please let me know if you have any questions.
Awesome. Thank you very much. I mean, I really enjoyed the presentation. I'm sort of curious. You mentioned optimizations on the previous one. Are there any pending optimizations that you have in mind that you would like to implement for these circuits?
Oh yeah, quantum ones. Yeah, I mean, that's a whole field of research in itself, right? Quantum circuit optimizations. There's a lot of essentially a lot of these boil down to graph rewrites, right? So these are really quite suited for well for MLIR, and yeah, I mean there's a large variety of them.
This is Mahesh here. Great presentation. I think a lot of it I don't understand because I don't really understand quantum computing and like the intricacies involved. So my question comes from that point of view. For somebody who is like traditionally worked on compilers, what are the steps to kind of understand things that you can use / leverage out of what rest of the ecosystem in MLIR is working on, and so that kind of have some visibility into what are the kind of things that you would want from traditional compiler systems that would work for you.
Right. So your question was, I guess, what a traditional compiler engineer would need to kind of understand in order to leverage
like
Catalyst.
Somebody who wants to work on compilers, if they want to work on, try to understand how they could start build. What are the pieces that from traditional compiler systems that could compile algorithms or traditional ways in which people do transformations for optimizations in compilers? What of that translates into your world of quantum compilers, and what doesn't? Kind of. Is my, if the question is dumb, I'm sorry, but I don't know much about it.
Yeah, I mean that's a great question. So right, so like what kind of techniques from traditional compilation can we use, right? And I think that there's a lot. So there's compiling for accelerators. So it's very active field right now, and scheduling computation. Distributing computation, like all these kinds of things, I think are certainly relevant. And yeah, I mean, how to deal, I guess, with I guess accelerator-based programming, where maybe you have to deal with kernels and interaction between host and accelerator. So I think these are certainly relevant.
So the follow-up there, the way you're looking at it is you're taking a program and you're trying to decide what part goes into like a traditional host CPU, GPU, and what part can be executed on a QPU as you had in your device. Is that part of what you're looking at?
Right, right. Yeah, that's certainly yeah, that's one of the big pieces there.
So could you give me an example of how you would make that decision? Is that something driven by the user or something that you can analyze,
Yeah,
make,
right.
program, and say this part works well on a quantum computer, and then
So it is mainly driven by the user, right? So because quantum algorithms are so different than classical algorithms, you're not just gonna take some classical algorithm and say, oh, this piece can actually execute on a quantum computer. The user will specifically write instructions for the quantum device. And of course, all those instructions need to execute on the quantum device. You can't really automatically write device code. If the user didn't specifically express the quantum algorithms, you're not going to see any kind of performance improvements.
Great. I mean, if there's no other questions for a speaker, I think we could perhaps follow some of these offline as well. Thank you for a great talk. You know, really appreciated this. You know, it's always interesting to learn, and someday I may understand the circuits better. But you know, looking forward to you know, future work here. And I think it would also be very interesting if there's anything infra related that you know, sort of like missing, given most of us who've been building like the infrastructure here have been focusing, you know, more on some of the classical models, you know, so if there's anything that like the needs come up from like the quantum side or representation side, you know, I think it would be very interested to know and to see, you know, where some of the gaps are. But yeah, beyond that, you know, I just like to thank the speaker, and then we'll have our next community meeting, well, pretty soon again.
Yeah, thank you so much for having me.
Thanks, everyone.